In this lesson, we're going to look at methods for approximating a definite integral. We're going to start off by drawing a set of axes. This is at the top of the page under rectangle approximation. Here's our x-axis. Along the way, I'm going to label this A and this B. Then I'm going to make some generic function f of x. That ought to do. F of x. Now my goal is to approximate the integral from a to b of f of x dx, and I'm going to do that by summing up a bunch of quantities which we're going to refer to as rectangles here. Alright, let's draw such rectangles. The first rectangle, what I'm going to do is just draw a slash. What's important about the slash is that the slash intersects the curve f of x at some point, and then I'm going to turn that into a rectangle. Very crude rectangle approximation. Going to draw another rectangle in a similar fashion, making sure that the curve intersects. Coming down. Another crude rectangle. I'll do another one. These are intentionally different lengths, and I'll do a final one that does something like this. Okay. These are not all the same width rectangles. I'm going to next identify the x value where the height of the rectangle occurs. So here's the height of the rectangle, and if I drop that down, I label the x value as C where the height occurs, and I'll call that C1 for the first x value where the first height occurs. My height is here. I'll drop it down. Yours does not have to be exact. It could be closer to the right or closer to the middle. Over here, I'll draw the next one. Again, this is the x value where the height occurs, C3. And then finally, this one turned out to be in the middle, C4. We have 4 rectangles, and I've labeled the x values where the height of each respective rectangle exists. Now back to the approximation. The integral from a to b of f of x dx is approximately the sum of these rectangle quantities. So I'm going to add up, so I'll show the sum, from k equals 1 to, in this case, 4, but in general it's going to be n rectangles. Each rectangle has a height of f of c sub k. So k will go 1, 2, 3, in this case 4, but in general up to n. And then the width of each rectangle is change in x sub k, the first, the second, the third, dot, 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 the nth. Also interesting to note that in the event that my curve was under the x-axis, then each of these f values would be negative, and then the sum would still approximate the definite integral. At the bottom, you may want to label what I mean by change in x. So this is change in x of the first rectangle, so that's change in x1. Then the next change in x is the change in x of the second rectangle. It's the width or the partition. Change in x of the third. And finally, the largest partition is change in x of the fourth. And again, in general, there are n rectangles that we could use to approximate the definite integral. Now for the trapezoidal approximation. I'm going to draw the same set of axes. Here's my x-axis. This is going to go from A to B again, and then I'm going to try to draw my function virtually the same, some generic swoosh function f of x. This time, instead of drawing slashes to represent the top of a rectangle, I'm going to draw points. Now these points don't have to be equally spaced. I just want to get a generic couple of points here along the curve. Now if I connect each of these points with a line segment, you can see that I am making a bunch of trapezoids. So I'm going to drop this height down, I'm going to drop this one down, drop this one down, and so the segment along the curve is the slant of the trapezoid. Sometimes the part of the curve goes over, part of the trapezoid goes over, sometimes part of it goes under. See here, I'm adding a bunch of these trapezoids. There we go. A little bit sloppy, but you get the idea that we have some trapezoids. Now, using the labels of C to identify X values, I'm going to come over here, I'm going to override the A, and I'm just going to call that C0. Then I'm going to look at the next part and call it C1, the next X value, call it C2, etc., etc. Now, if I kept going, I want to make this one out here a generic one. So maybe this is C sub K. And then if I go to the very last one, I override B to be C sub N, the nth X value, and the one before that would be C n minus 1. We also have partitions of X, so we have our first change in X, change in X1. We have our second change of X, change in X2. That's a little hard to write that, but at some point, let's do one more. Let's do change in X3. Boy, that just looks awful. Hopefully you see the change in X1 is here, change in X2 is here, change in X3 is here. Out here, I have change in X of the nth interval. And over here, I could say change in X of the kth interval. So let's approximate the integral from a to b of f of x dx by adding up a bunch of trapezoids. I hope you see that. Let's highlight the first trapezoid. So that first trapezoid is on its side. We've appealed to geometry before, and we're going to write the formula for the area of the first shaded trapezoid. So my first base, my base 1, can you identify what base 1 would be? Hopefully you're saying f of C0. And then we need to add the second base, which is f of C1. And I need to average the base. Then I need to multiply it by its height, which turns out to be this change in X partition. Change in X of the first partition. Now I'm going to go and add the next trapezoid to the right. So that will be this trapezoid here. The first base of that trapezoid is f of C1. And then I'm going to add the next base, which is f of C2. Divide by 2 again to get the average base, times the height would be change in X2. Oh, I want to do another one. I can't help myself. F of C2 plus f of C3 over 2 times change in X of the third partition. That would be the third trapezoid. I want to keep going though, so I'm going to say plus dot 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 plus. Now, see if you can tell me the area of the second to last trapezoid here. Can you figure that out? That's going to be f of C sub n minus 2 to give us this base here. Then I need plus f of C sub n minus 1 divided by 2 times change in X of the nth minus 1 interval plus, now finally, the last trapezoid, the last guy here, is going to be f of C n minus 1 plus f of C sub n all over 2 times change in X of the nth interval. So this formula that you see here, or process that you see here, always works. So this always works. You can always use that process. It works when change in X is constant, meaning the partitions of X are always the same. It also works if change in X is not constant. It always works. I would, however, like to explore what would happen if change in X was always the same. So come over to this formula that we developed And think about what can we do mathematically if change in x is the same for every single trapezoid. Hopefully you're thinking you can factor out that change in x if indeed it is constant. The other thing that you can factor out is a 1/2. Notice that everything is divided by 2. And if I factor out change in x and a 1/2, then I'm left with some other items. I'm left with f of c naught. But then what am I left with? Do you see here that we're going to have f of c1, but then we're going to have another f of c1? That means we're going to have 2 of the f of c1s. Would like to come up here and look at that for a moment. So this first trapezoid has this base over here. But the second base, I need a different color, the second base over here is going to be shared with the trapezoid to the left and the trapezoid to the right. In fact, all of the ones inside will be shared. So we'll have 2 times f of c2 plus 2 times f of c3 plus ... and that pattern continues. Over here we're going to have 2 of the f of c sub n minus 1s, 2 times f of c n minus 1s, and finally this item at the end, this last base, is only a singleton, f of c n. The endpoint bases are singletons, and then the ones in the middle get doubled. In our formula below, the author of your textbook says it's change in x over 2, but instead of saying f of c naught, they simply say y naught plus 2 y1 plus 2 y2 plus ... plus 2 y n minus 1, finally the last y value, y n. And that's the formula that appeared at the top of this section.